Carbon-12 is the most abundant isotope of carbon, but it is not NMR active. Carbon-13, the heavier isotope of carbon, has a spin quantum number of 1/2 and is NMR active. Only 1% of all carbon atoms are carbon-13. Therefore, no single molecule gives rise to all the expected carbon NMR signals. Many molecules contain no carbon-13 at all. The large number of molecules in a sample, however, ensures that the NMR spectrum contains the signals for each carbon position with the same probability. In a 300 MHz NMR spectrometer, proton resonances occur near 300 MHz. Carbon-13 resonances on the same instrument occur near 75 MHz. Because of this large separation, we can observe carbon-13 and hydrogen without interference from each other. Chemical shifts for hydrogen fall within a window of from 0 to 10 parts per million, and peaks often overlap. A carbon spectrum spans a much wider range, from 0 to 230 parts per million, and consequently, peaks rarely overlap. The chances for two carbon-13 atoms to be adjacent in a molecule are slim. Therefore, no significant carbon-carbon coupling is observed. Carbon-13 spectra are usually acquired proton decoupled, which means that the carbon-hydrogen coupling is suppressed. In a carbon-13 spectrum, every NMR signal is a singlet, a single peak. The only exception is the signal of deuterochloroform, an NMR solvent. It appears at 77 parts per million as a 1-1-1 triplet due to carbon-deuterium coupling. Carbon-13 is not very abundant. Additionally, it has a weak magnetic moment. Carbon-13 therefore gives rise to a relatively weak NMR signal. As a consequence, carbon spectra have a much noisier baseline than proton spectra. In a proton decoupled spectrum, the signal of carbon-13 is enhanced through the nuclear Overhauser effect, or NOE. Only carbons attached to hydrogens experience a significant NOE enhancement. The more hydrogens, the stronger the effect. Carbons without attached hydrogens, such as carbonyl carbons, experience little NOE enhancement, and therefore give rise to relatively weak signals in the spectrum. This enhancement distorts the intensities in a carbon-13 spectrum and makes integration of the spectrum meaningless. In carbon-13 NMR, distinctly different chemical shifts are observed for aliphatic, aromatic and alkene, and carbonyl carbons. Within these regions, precise peak assignment is, however, often difficult. Even unsubstituted aliphatic carbons resonate over a wide range, dependent on whether they are primary, secondary, tertiary, or quaternary. Carbon chemical shifts are further affected by long-range effects caused by the other carbons in the molecule. Even non-adjacent carbons strongly influence the carbon-13 resonance frequency. An electronegative substituent not only de-shields the alpha carbon to which it is directly attached, but also, to a smaller degree, the beta carbon. Unsubstituted carbons appear at the upfield end of the spectrum, between 8 and 60 parts per million. Weak electron withdrawing substituents cause a downfield shift to between 20 and 65 parts per million. Strong electron withdrawing substituents cause a downfield shift to between 40 and 80 parts per million. sp2 hybridized alkene and aromatic carbons can easily be distinguished from aliphatic carbons due to their higher resonance frequency. Again, neighboring carbon atoms and substituents influence the chemical shift in a complex manner. In molecules with triple bonds, the induced local magnetic field shields the carbons, leading to a lower resonance frequency. Carbonyl carbons, which are sp2 hybridized and adjacent to an electronegative oxygen, have the highest resonance frequencies. Carboxylic acid, ester, and amide carbons resonate between 160 and 185 parts per million. Aldehydes and ketones resonate between 190 and 220 parts per million. In nitriles, the local magnetic field shields the carbon, causing a lower chemical shift of between 110 and 130 parts per million.